Welcome to another video. This is video number 6, I believe. Yes, or 5. I think it's 6. Now I've lost count. But this is the next video in the series, and in this video I am going to explain to you all these terms that tend to confuse students, including terms that I've already explained, like the domain, the null space, the kernel, such words like that. I am going to explain all of them. Okay, but I'm going to use an analogy that you can relate with. I am going to treat this as if it is a school bus. So the linear transformation, I am going to call it transportation. The school is going to be the domain, and home is going to be the codomain. But the home appears to just be some village where you have a group of women who have kids at the school, and the Grinch, who has no kid at the school, which is 0, or may take some of the kids. This is how I always imagine linear transformations. I imagine a school that has a bunch of students, kids, little kids. Let's imagine it's an elementary school. You have tiny little kids, not tiny, they're no longer tiny these days, but you got very young kids, like, let's say it's even a nursery school. No, elementary school, better. And these are all the kids. By the way, I just had to label, maybe I should call this, maybe this is now 10, 11, all the way to 15. Okay, so many. Let's just say I have 15 of them in that school, okay? There could be a finite number or an infinite number, but just understand that also, I'm just trying to do an illustration for you to understand these terms, including the kernel. Okay, so you have the school, which is the domain, and all these kids are vectors, okay? Now, you have a school bus, which transports kids to their homes or wherever they're supposed to go to at the end of the day. So the school bus takes vectors from V, from the school, to W, which is the village, okay? The school is the domain. The village is the codomain, okay? Where all the kids go toward is the codomain. Now, what is the difference between the range and the codomain? Because the range is part of the codomain, but it is not the codomain. Now, look at this village. These are all women who have kids in this school. At the end of the day, every day, they wait at the bus stop or wherever they get the kids and wait for their kids to come, okay? Not every woman in the village has a kid in the school, but they might just all hang around, you know, playing together, and then when the school bus arrives, say, "Oh, that's little Johnny, how you doing?" And Johnny goes to his mother, but Johnny does not go to, let's say, the woman number 3 does not have a kid who goes to that school. This woman number 3 is not part of the range, even though the woman is part of the village, the codomain. So the range is strictly the set of women in this village that have kids in the school that the school bus brings home. That is the range. So the range could be the entire codomain, or it could be less than the codomain, but it is not the same thing as the codomain. So if you want to define the codomain, it is basically the vector space to which the linear transformation maps. It does not mean everybody in that codomain has some vector that is mapped to it. Okay, we got that one down. Second thing, the range is the set of vectors in the codomain that have kids in the school that are mapped to it. So I'm going to write those definitions, but I want you to see the difference. Okay. What about this guy, the Grinch? Let's call Grinch the zero vector. Okay? The Grinch is the zero vector. Sometimes the kids that come on the bus, unfortunately, do not have mothers waiting for them. They don't have any of these women is not their mother. They have to go live with the Grinch. The set of kids that must be taken to the Grinch are what you call the null space or the kernel. They all go to 0. So call this guy the zero vector in the village. The Grinch is the zero vector in the village. So every transformation that leads to 0 is such that all the kids that go to the Grinch, they go to 0 in the codomain. That set of children or vectors that go to the Grinch are called the vectors in the kernel. They are in the kernel of the transformation, or they are in the null space of the transformation. Good? Okay. What else is there to explain? Well, you know this is the domain. Okay, something you must learn. Remember we said linear transformation is a function. And what characteristic of functions must you retain? Every function is such that it maps one item, one input to one unique output. Just as you cannot have one child have two mothers. It is impossible. A child cannot be mapped to two different mothers. Every child must be mapped to one mother. That's why a linear transformation is a function. Okay? So note that every child maps to a single mother. If there is no mother, then it goes to the Grinch. Okay. Makes sense? Remember, one of these mothers does not have any child here. So this mother here is not a part of the range, even though it is part of the codomain. The Grinch is part of the range. Unless there is nothing that maps to 0, but that's impossible. Because the 0 vector is in every vector space. And if this is a linear transformation, the linear transformation of the 0 vector must be to the Grinch. So the Grinch son is the 0 vector that's living here. So the Grinch will always get his own child and might get other children also. Remember, every child that goes to the Grinch is in the kernel of the linear transformation. I hope this explanation is clean. Okay, now let's do one more. What about when the linear transformation is 1 to 1? Like I explained, every child must go to a single mother. A child cannot go to two different mothers. It's not possible. It doesn't make sense, right? Otherwise, this will not be a function. But when is a linear transformation 1 to 1? All it says is that if there is a linear transformation of a vector and it maps to W1, and there is another vector, vector 2, and it maps to W1. So, is it possible that you have two different kids go to the same mother? Yes. In fact, that happens often. But that's not a 1-to-1 function because one child must go to one mother, one child to one mother. You cannot have two children going to the same mother. If that happens, it is not a 1-to-1 function. So if it ever happens that vector 1 goes to W1 and V2 also goes to W1, then it means that V1 must be equal to V2 if the linear transformation is 1 to 1. These two must be the same vector. If they're not the same vector, then it's not 1 to 1. That's the meaning of 1 to 1. You can always see it or work it out. Okay, now what is onto? This is the one that always throws students off, including me. Well, then, but now I understand it. A linear transformation is onto. Listen up. A linear transformation is onto if all the women in the village have children at the school. That's it. So this lady that doesn't have a child at that school would not be here if this was an onto linear transformation. Onto means for every W in the codomain, there exists some V, some child in the school, such that the linear transformation of that vector must come to that W. It means when you look here, it is onto because everybody here has a child there. So let me give you where the confusion might come up. So let's say there are 15 children at the school and there are just 4 women. And the Grinch is also there, don't forget. You might have a case where this woman has 7 children at the school. This woman has 1 child, this one has 1 child, this one has 2 children. 7, 1, 1, 2 is basically 11. So 11 children will go to these 4 women. That's it. As long as these 4 women have children in the school, it is onto. It doesn't matter how many children the Grinch has. But you notice that out of 15 children, if they have 11, the remaining 4 children must come here. So that's the entire concept of codomain, range, one-to-one, and onto. I'm going to write the formal definitions of all of these terms, and then we just take an example of a linear transformation and find out if it is one-to-one or not one-to-one, if it is onto or not onto. I have this problem here, and I think this was a previous one that I used to establish the kernel. I remember the null space, but let's just use it to find the range. Now, the question is, what is the codomain? What really is the codomain? Okay? The codomain is always this guy here, is R2. What is the domain? The domain is R3. So the domain is, this is the domain. Is this guy here. You know how we draw X and Y axis and then the Z axis? Yeah, something like this, where this is we can call this Y, call this Z, and call this the X axis. Okay? So you have the 3D kind of picture of what the axis should be, if you can see it. Okay? So we're taking points or vectors from here, and we're mapping it using this transformation into where you're going to have just X and Y. So we're taking it into just this plane. So we're just taking it into this plane where you have Y and you have X. So anything here is going to go here. So the domain is R3. The codomain is R2. Now, that's the first one. So this is the domain. This is the codomain. Now the Grinch is here. 0. So even if nobody is mapped, even if you pick a point here and it doesn't map to 0, this guy must map to 0. The Grinch's son is here. The 0 vector must map to 0 if this is a linear transformation. Otherwise, it is not a linear transformation. If 0 suddenly becomes 1, there's a problem. Okay? So 0, 0 must map to 0, 0. Okay? Now, this can also map to 0 depending on the kind of linear transformation that we are performing. Okay? So, but let's say this guy does not map to 0, then it must map somewhere else following this rule. The rule is A1, which is this, minus this is how you're going to find this. And you're going to find this one by multiplying the third component by 2. So, what is the range? The range is the set of all vectors that look like this a1 minus a2 to a3, which can be anything. In fact, every single number, every single point satisfies this condition. Okay? So there's nothing I can say that's special because you can generate any number by subtracting one number from another number. Any number can be generated, whether it's rational or not rational. How can we find pi? Well, it's going to be 2 pi minus pi. That's pi. And because 2 pi is real, you can write this as pi. How can we write this? Can this be pi? Yes. If a sub 3 is half of pi, half of pi times 2 is pi. So you can have any number. There are no restrictions. It doesn't matter what you want. So we can say in this case that the range is all of R2. Because there are no exceptions. There is no number you cannot create. There is no pair you cannot form. Because you're going from R3 to R2, following these rules. See, this is where it becomes crazy because you have to know what you're talking about. Okay? So what is the kernel? We already did that in the last video, or maybe the very first video when I talked about kernel and null space. So the kernel is whatever we make this 0, it means A1 must be equal to A2, and this must be 0. That's how you're going to get 0, 0. So if this is some x, this is x, then this is 0. Any vector that looks like that, where these two are the same and this is 0, is going to give you 0, 0. And that's what you call the kernel. Previous video. What else do I need to explain? Oh, one-to-one and onto, which is the main crux of this video. So is T one-to-one? Now, obviously, T cannot be one-to-one. This is why it cannot be one-to-one. Let's say the woman that's on this side is 1, 3. Or let's make it even to make it easy for us. Let's call it 1, 4. Okay? How did we get this? Well, according to this rule, we multiplied A3 by 2. So A3 must have been, on this side, the vector that was transformed must have had this third component be 2. Now, so that one is easy, right? Because it's just A3 multiplied by 2 is what gave us this one. But how did we get 1? Is there only one way we can get 1? Remember, what you have here is obtained by subtracting A sub 2 from A sub 1. So how many ways can we get 1 by subtracting two numbers? There are infinitely many ways. It could be 1 minus 0. It could be 2 minus 1. 3 minus 2. You see, there are so many ways, so you cannot say it is one-to-one. If there's a child that is 2, 1, 2, you will get this answer when you do the linear transformation. Because it's 2 minus 1, 2 times 2. And that's what you're going to get. What if the child is 3, 2, 2? What if the child is 5, 4, 2? So there are many children that are coming to this mother, therefore it is not one-to-one. Okay? So it's easy, you just have to give an exception. Okay? If you want to say, is T one-to-one? The answer is no. Because the linear transformation of, you can just do 1, 0, 2 equals what I just did, 1, 4. And the linear transformation of 2, 1, 2 equals 1, 4. But, oh, I didn't tell you. That's it. But 1, 0, 2 is not the same thing as 2, 1, 2. So by definition, I should have given you the definition first. T is one-to-one. If, actually, and only if, it is an if and only if situation, that T is one-to-one if and only if T of V, let's call it T of V1, equals T of V2. If these two are the same, just as we have these two are the same, the linear transformations, if they are the same, then it implies that V1 equals V2. This is the simplest way to present linear transformation. You can only claim that T is 1 to 1 if and only if the equality of their images, these are called images, okay? Oh, I didn't say that word. It's image. The set of images is the range, okay? If the equality of their images means that the pre-images are exactly the same. What did I say? Pre-images? The vectors that were transformed are exactly the same. But that's not true in this case. Therefore, T is not 1 to 1 because this and these are not the same. That's how you show 1 to 1 in any case. Now, so this is not 1 to 1. We already said no, not 1 to 1. Now let's do the last one. Is it onto? I'm going to use this space and then I end this video. Now, I will not make the mistake I made here. Is T onto? The answer is yes. How do you know onto? I'll give you the definition. T is onto if for every W in the codomain, for every output in the codomain, okay, there exists some V in the domain such that the linear transformation of that V is equal to W. That's the meaning of onto. Let me go over it again. Remember what I said about onto. Every woman in the village has a kid in the school. So we say T is onto if for every W in the codomain, every woman in the village, there exists some kid in the school such that the school bus will bring the kid to the woman by law. That is what you call an onto function. For onto, you start from the codomain and research to see if everybody in the code, every single person in the codomain has a kid. For 1 to 1, you're going to talk about two kids that go to the same woman. It's possible. If two kids go to the same woman, then those two kids must be the same kid. If they're not the same kid, it is not 1 to 1. Make sense? That's it. So let's see this. Is this onto? Well, look. This can give you any real number. This alone will give you any real number since A is any real number. You can generate any real number by subtracting two real numbers. So there is no vector you can create that does not have A1, A2, A3 in R3 that can generate it. Okay, there's none. There is none. Okay? So, because this is real, all real numbers can be generated by simple subtraction of other real numbers. Okay? And any real number can be generated by multiplying another real number by 2. So, every single vector in the codomain can be generated or can be formed using these real numbers in the domain. Therefore, every single vector here is in the range. And if the range is equal to the codomain, then you say it is onto. Every woman has a kid, including the Grinch. Remember, the Grinch has its own kid. It's the origin. It's 0, 0. Okay? And that's it. So is it onto? The answer is yes. So let's call this B1, B2 equals A1 minus A2, comma 2A2, A3 rather. Every B1, B2 can be computed using appropriate real numbers. Now, my final answer may not be the most mathematical presentation, but this video was to explain the concept to you, okay? If I don't sound mathematical enough, forgive me. I'll see you in the next video. Never stop learning. Those who stop learning, stop living. Bye-bye.